Dawn earned her PhD in statistics from Duke, after which she was a faculty member in the Operations Research and Information Engineering School at Cornell. And she developed forecasting methods for emergency vehicle decision support systems, in fact, in collaboration with the ambulance organizations. After which she decided to leave the cold Cornell and go to the rainy Washington, I guess, rainy Seattle, to join MSR on her sabbatical, and creating travel time prediction methods to use in Bing Maps, and then finally is at Uber now. And unless you were in MSR somewhere else, which you can correct me later, Dawn. So
no, that's right. Thank you.
All right. At this point, Jackie, over to you.
Many, many thanks to the organizers for everything that it took behind the scenes in order to make this happen. I'll be talking about mobility and transportation at a time in which those things are incredibly difficult. However, the geospatial technologies that I'll be talking about today are also broadly used in Uber's other lines of business, like Uber Eats, our grocery delivery service, and Uber Freight, our long-hauling service. In fact, that's one of the things that's gone well for Uber in the pandemic, is that because we've made these heavy investments in the platform technologies, that when we need to spin up a new line of business, like grocery, we're able to plug and play. The geospatial technologies are broadly used in user-facing apps like Google Maps and Waze. They're also the foundation of decision systems for many different kinds of applications, like ride-hailing, Uber, DD, Lyft, etc., and vehicle fleets, like ambulances and other emergency medical services, delivery fleets, and more. I've worked with a couple of organizations in this context, Bing Maps, for example, on their consumer-facing product, with Toronto Paramedic Services, which is an ambulance organization, on their fleet management, and of course with Uber. This is the Uber Maps data science team. We work closely with engineering to develop the technologies that I'll talk about today. So first I'll introduce geospatial technologies in the ride-hailing context, and then dive into two particular problems: route optimization and travel time prediction. I'll give a couple of examples of how times and routes are integrated into the experience and into the decision systems. When you as a rider open the app and put in a destination, you see the pickup time, for example. Here it's 2 minutes. You see the drop-off time, 9:43. And you also see the predicted route that the driver will use to get you to your destination. Additionally, in many regions, we provide an upfront price, shown here, on the request screen. And this is based on the predicted route that the driver will take and the time and distance associated with that route, whether or not there are any tolls and other factors. These technologies also power the back-end decision systems for Uber. Most critically, our matching or dispatch system. When a rider requests a trip, they're matched with an available driver. For example, we can batch multiple ride requests and multiple drivers together at the end of some time window and repeat for each brief time window. This involves a sophisticated optimization algorithm, a bipartite match. What's important about this is that the subjective function includes the predicted pickup time for the rider. And so the quality of these matching decisions and the efficiency of the platform and the service rely very heavily on the accuracy of these travel time predictions. Routing and times also are critical for Uber's turn-by-turn navigation service. This is in-app provided to drivers. It obviously provides several suggested routes, along with the predicted times and the turn-by-turn directions for those routes. So to create all of these technologies, we need to be able to provide an optimal route in some sense. So given an origin and a destination and a start time for a trip, we need to find a route that optimizes some combination of objectives. That includes time, but also includes distance, the road classification. Is it an arterial road, a major road, a highway, an alleyway? The types of turns. Are there many turns? Are they left-hand turns, etc.? So this is obviously used for turn-by-turn navigation. It's also used for upfront price because we have to predict what route the driver will take, regardless of whether they'll use in-app navigation or some out-of-app service or no navigation at all. So what's difficult about this problem? We have a very large road network and a combinatorial number of routes from point A to point B. And so from a computational perspective, it can be challenging. Additionally, we have to choose the objective function. How do we weigh these different objectives together? How do we combine them? Once we have a route, we need to be able to predict the travel time associated with that route. So given a route and a start time, predict that travel time. This is used obviously for the matching algorithms, as well as the calculation of that upfront fare for the riders. It's difficult because there are so many routes. We actually have a data sparsity issue. People think that because there's a lot of this location data, that there should be plenty of data on which to estimate traffic. However, if you look at any particular route, there may be little or no historical data for that route specifically, although there might be plenty of data on individual road segments in that route. The travel times also depend heavily on time of week, traffic, events, and more. So to summarize, in the life of a trip on Uber, ETAs, times, and routes are used at many, many different locations. When the rider opens the app and puts in a destination, they see that time to destination, they see the upfront fare. At the time of dispatch, we have to make that matching decision, which requires many calls to the mapping engine for potential matches. After the dispatch, we navigate the driver to the pickup point and then navigate the driver from the pickup point to the drop-off. And similar information about the route and the time to destination are provided in the rider display. So how can one do this? The critical data sources include the location trace data from historical trips. So here's an Uber example. This is a sequence of estimated driver locations by time during a trip. And you can see there's a bit of GPS noise in this particular trace, but that is fairly obvious what route the driver took. This type of location trace data is the only data source currently available that really achieves broad coverage of the road network. So there are other kinds of data sources like fixed sensors in the roadway, loop detectors built into the road surface, cameras that also measure traffic. However, those types of fixed sensors tend to be available only on a small minority of road segments, whereas we need to be able to estimate traffic and travel speeds for the entire road network. And the main source for this location trace data is mobile phones for many, many transportation and mapping applications. So again, this is the observed traffic in the San Francisco road network during rush hour. And I'm colored according to the estimated speed based on this location trace data. Red means that the estimated speed is much lower than the free flow speed for that segment, while green means that the estimated speed is close to the free flow speed. So you can see that there's traffic congestion on one highway, but not on the other. In addition to location trace data, we also need information about the road network itself. For example, OpenStreetMaps is an open source data set for streets and road networks globally. This data set includes information about each road segment. How many lanes does it have? How do those lanes connect from one road segment to the next road segment? What is the speed limit? What's the road classification? Is it one-way or two-way, etc.? Additionally, we need contextual information. Time of week has a very heavy effect on traffic and travel speed effects. Weather and events also really impact speeds. So here I'm illustrating the average speed by time of week for highways in San Francisco. This is pre-COVID data, and you can see that there's considerable traffic congestion, lower speeds during morning and evening rush hour, Mondays through Fridays. You see that Fridays have a slightly different pattern, and that weekends, Saturdays and Sundays, have an entirely different pattern. So how might one do route optimization using these various data sources? This requires three components. We have to be able to optimize an objective function. That's both difficult from a computational perspective, and we also have to choose the objective function itself. That objective function will heavily involve speed and time, so we have to have accurate speed predictions. And all of this is built on top of a graph that represents the road network. So how do we pick an objective function? There's a wonderful paper by Daniel Delling and colleagues from Microsoft Research in the mid-2010s. The key takeaway here is that the fastest route from A to B is not necessarily the best route. Drivers care about many factors, not just time, but also distance, the types of turns, the number of turns, the types of roads. Are they highways or non-highways? Are they alleyways, etc.? They care about safety. Complex maneuvers can be challenging from a safety perspective. So on the left, I'm showing a left-hand turn versus a right-hand turn. Some left-hand turns can be slow and stressful for drivers. So it's important that we learn that and take that into account in the objective. On the right, I'm showing an alleyway in San Francisco. Alleyways, although sometimes they're faster, can be higher variance in terms of the speed if drivers can get stuck between behind a parked vehicle, for example. They can be stressful if the driver has to exit an alleyway onto a major road. So Delling and colleagues frame this problem in terms of finding an objective function that leads to routes that drivers are likely to follow. They frame their objective function in terms of combining these different costs. They do so by adding across the road segments and the turns of the route. Within that additive objective, they use some combination of time, distance, etc. The fact that this objective function is additive really matters for the computational techniques that we can use in order to calculate that fastest route, that optimal route. It turns out that it's much more difficult to do for non-additive objective functions, which is why they make this choice. So here are a few example routes from Uber. You can see the fastest route in purple is much longer than a route that uses a weighted combination of time, distance, etc. That weighted combination leads to a time from the origin to the destination that's very close to the fastest route, not quite as fast. So a small sacrifice in terms of time makes it a much more desirable route from a driver perspective because of the lower distance. So how did these authors learn the function f in their objective function? They want to produce routes that are similar to actual traces that drivers have taken, actual routes that drivers have taken. So they define what's called a route quality score. The proportion of the actual driver trace, which is close to the optimal route according to some specific function f. And then they search over different functions f in order to maximize the average route quality score. They do this using a set of historical vehicle traces. So once you have an objective function, how do we do that computation? So this can be framed as a shortest path calculation on a road graph with weighted edges. Roughly speaking, in this road graph, the intersections are captured by the nodes and the directed road segments are captured by the directed edges. The turn costs can be represented as tables associated with each of the vertices. And so in this framing, we can use standard calculation of shortest path. You're probably most familiar with calculations like A star, bidirectional search, etc. And keep in mind that all of these algorithms assume that the objective function is additive across the road segments and the turns of the route. More recently, there have been developed a variety of methods that scale much more efficiently to even continental scale road networks. These include what are called contraction hierarchies and customizable route planning. Non-additive objective functions are a much harder beast. However, they might be desirable in some contexts. So if, for example, we're less interested in minimizing the expected time from A to B, and let's say we want to instead be more risk averse and maximize the probability of an on-time arrival, that is not an additive objective function across the road segments. And so it leads to a much harder computational problem. Typically, we restrict ourselves to these additive objective functions so that we can easily scale to continental scale road networks. Once we can do optimization, we need to have these predictions of speed or time at the road segment level. And so this can be done in two stages. It's done using the location trace data, both historical data and real-time data. It's done through two steps. First, map matching the trip location traces, and then doing segment level travel speed prediction using those map matched traces. So map matching means estimating what route the driver took and how long they spent on each road segment. So here, this is the example from before. There's a bit of GPS noise. However, we've estimated the route in black. And we also estimate the amount of time spent on each road segment, shown in purple. Once we have this, we can do segment level speed prediction using standard machine learning techniques fit to the segment level travel time observations. So this is reminding you of that data source that I talked about before. That's the data source at the segment level that was used to generate this plot of travel speeds in San Francisco during rush hour. So fitting a machine learning model to these segment level travel speeds or times can use many features, including the real-time estimated speed for this road segment. If, for example, there are multiple traversals of this road segment in the last 5 minutes, 10 minutes. We can also use the historical average speed for this road segment at this time of week. That captures weekly traffic patterns. We can include the road classification. Is it an alleyway, for example? The speed limit, the time of week, weather, events, etc. And Bing Maps uses precisely this kind of approach for its speed prediction and routing, and there's a nice article that describes that. All of this is built on top of a road graph. What do we do if the information in that road graph is incorrect? You can detect those types of errors in many cases using that same location trace data. So here's an example where there's a missing road segment. and it leads to the estimated optimal route being very long, 7.5 minutes. Whereas if we know that that segment exists, the route is only 30 seconds. So how do we find and fix such mistakes? Here's an example. With the blue dots, I'm showing the location trace of the driver. In red, I'm showing the map-matched route, the estimated route based on our roadmap data. You can see that there's a discrepancy, a deviation between the two. That might be caused by GPS noise. However, it might be caused by us missing a road segment in the road network. Another example is the case in which the recommended route is different from the route that the driver actually took. So in this case, in blue, we're showing the location trace. In red, the map-matched route for that trace. And in black, the recommended route that we provided to that driver. The driver didn't take a left-hand turn when we recommended one. If we see that many drivers do this, ignoring a particular turn, that suggests that there might be a turn restriction there that we don't know about. Uber has used automated algorithms to detect and fix about 600,000 errors globally in base maps. I'll talk a bit about the accuracy of these. The precision of our algorithms is currently about 75%. That's measured by automatically detecting these errors and then sending them to a human operator to determine whether there is strong evidence that this is in fact a base map error and needs to be fixed. And that's where we get this estimate of 75% precision. It's harder to measure recall because we don't know where the base map errors are in the road network. There might be many that we have never detected or that we don't have any evidence for. And it's difficult to get a human operator to tell us that there's a mistake in a base map when there's no location, trace, evidence of such a mistake. So it's very difficult to measure recall. So success can be measured using a combination of precision and the volume of errors detected. So although precision of 75% may not sound very high, keep in mind we're better off casting a broad net and finding more errors and then allowing human operators to determine which of those errors are valid and need to be fixed. Here I'm showing the different types of errors that we've fixed. There are missing road errors. I mentioned that before. There can be road closures, which we want to detect very quickly and then block off in the roadmap. There can be mistakes in turn restrictions, which I illustrated earlier. We can have an incorrect directionality of a road segment. For example, thinking that it's a one-way street when it's a two-way street. Sometimes we find and delete road segments that no longer exist. Let's talk about travel time prediction once we have that optimal route. The simplest thing to do is simply to add up the predicted times from the individual road segments and turns of the route. However, it turns out that this is not the best thing to do. It's certainly computationally scalable. It captures the road network information. It captures physical dynamics associated with fine scale traffic patterns. So there are a lot of advantages. On the other hand, because we're modeling at this fine geographic granularity, the road segments, the errors tend to accumulate as we add across the road segments, adding noise. Additionally, because we've taken this multi-stage approach through map matching and traffic estimation, routing, and adding up the speeds across the segments, this type of multi-stage approach can introduce bias as well. And so how can we address these challenges of variance and bias? Now, just to illustrate this point again, notice that the geographic granularity, these road segments at which we are modeling, can be very, very short, whereas the trips might include a large number of sequences of road segments. The solution here is to combine a trip-level machine learning model with this type of segment-level machine learning model. There's a wonderful paper out of DD's research labs that describes a method to do exactly this. There are a variety of other methods as well that I won't describe. So just to illustrate the fact that you can do trip-level modeling and segment-level modeling, here are lists of potential features that you can put into either of those models. The trip-level models, including, of course, origin and destination location, latitude and longitude, the time of week, the month of the year, holiday or an event, etc. And then, of course, the segment-level features that we've already discussed. So Wong and colleagues in this DD research lab combined 3 models, 2 of which are trip-level models, and 1 of which captures segment-level information. And so these trip-level models capture global statistical information, geospatial patterns at a coarse scale. One of the models they call a wide model. This is a classic statistical model, a generalized linear model that includes many interaction terms between the features in the model. The deep model is a deep neural network with the same set of features. It captures even richer interactions of those trip-level features. And finally, they have a model that captures the segment-level information, and they do so using a recurrent neural network structure. Now, this is natural because the number of segments in a route can vary across different routes. So like a spoken sentence in which the number of words differs across different sentences. So you can capture the sequential structure and the segment level features using this recurrence. And then you can combine the outputs of these 3 models using a regressor to get your final prediction. And so they apply this to a very large data set from Beijing, 500,000 drivers and road segments. And they get accuracies that are about 5 or 10% better than totally generic trip-level machine learning approaches. So the bottom line here shows the results from the DD research paper. And the 2 lines above it show the accuracies for competing trip-level machine learning models. The top line shows the accuracy of an approach that, roughly speaking, sums the predicted times across the segments and intersections of the route. You can see that you get about 5%, 10% improvement over the trip-level machine learning models, and an even bigger improvement over the segment-level summed approach. And so to conclude, we've talked about key geospatial technologies for ride hailing. These include route optimization and travel time prediction. In order to do these well, we have to capture both micro-level effects at the road segment level, small-scale traffic effects, for example, as well as macro effects at the trip level, large-scale geospatial phenomena. The primary data sources available are location traces, the road network data, and contextual information, like time of week. Thank you. Happy to take questions. We are hiring at all levels, and more information is available on my website.
Thank you, Jackie. Thank you, Don, for this excellent talk. There are a few questions. I think I will start with this one. Thomas says, he's asking a question about if mobile data is a strong data source used to build these, how are new markets bootstrapped when there's not a large amount of historical or prior app data?
Yeah, that's a great question. It's important to keep in mind that a lot of the features that I described in machine learning models, for example, the segment level features like distance and road classification, et cetera, actually are generic and are available in cities where we haven't previously gathered data. Some of the features at the segment level have to be estimated using data from that road segment, which is where this particular challenge comes in. Even at the trip level features like route distance are available even for areas where we don't currently have mobile data, right? So it's actually possible to fit a global model based on the generic set of features and some surrogate features like estimated or average road speeds in a particular road class with a particular speed limit. For example, there are ways to fit global models using generic sets of features, both at the segment level and at the trip level, and then to apply those models in an area where we don't currently have mobile data.
Great, thank you. There's a question from Anant. Anant asks, often the actual driver routes can be systematically wrong, and I think what he means is